last class for this year. Physics last class, right? Yeah. Okay, guys. Moving ahead here. Uh, till now, let me have a very quick recall of what you have done till today. Okay, for this chapter. So we know what is an induced EMF. We know what is induced current, the power dissipated. We know induction, self-induction, mutual inductance. We know eddy currents. We know back EMF. Right. So we have learned many of these things already. And today I'll be talking to you about generator and transformers. So once generator and transformer are over, we can go ahead with the problems, because from last many days I didn't solve any problems. I was just teaching you the theory, right? So we'll move ahead as soon as possible. Hello there from YouTube. Hi. Okay, cool then. So before we starting into this problem, let me have a very quick recall of two formulas which you already know, right? So one is called a self-induction. What is self-induction? Self-induction is the induction happen in same coil. There will be one single coil, and if this single coil opposes the change in current, that is called a self-induction, and it's given by letter L, and it is equal to N square mu naught A by L, right? Where N is the total number of turns, where mu is the permeability, A is area, and L is length of the coil. So this is self-induction, which happens in the same coil. So, and we know mutual inductions, which is there is one coil, primary coil 1, and there is primary coil 2. Right, when current is flowing in coil 1 and current is induced in the other coil, this is called as mutual induction, because the induction is happening in a different coil, right? So that's happening uh, completely in a different coil. So then I can say that mutual induction M is equal to N1 N2 mu naught A by L. Am I right? So I hope you all of you know these two formulas. We'll be using them a lot today. Okay. Good afternoon, everyone from YouTube. Awesome. Good afternoon, everyone from Zoom. Cool, guys. So shall we go ahead? Once if you know these two formulas, we can go ahead with the next concepts without any problem, right? So we derived this formula, right? So remember that also. After completing the chapter in half an hour or so, I'll revise the concepts of all the chapter completely. I'll write down all the formulas of the chapter. Then we'll move on to solving the problems. Okay, few important problems, not all, but let me solve 5 to 6 problems which are very high probable for the JEE and NEET exams. Okay, cool, guys, awesome. So, and very simple concept is resonance, not resonance, sorry, induction in series and parallel. So what happens if if I connect an inductors in series? So you might already know that if I connect resistor in parallel, the formula will be R is equal to 1 by R1 plus, sorry, R is equal to R1 plus R2 plus R3, so on. It moves ahead, like as many resistance are there, so we can move that many formulas. Sorry, Krish, my internet is slow, and the lightning is very bad here, so I'll just switch off my video. Okay, no electricity, bro. Okay, cool then. So, and we also know that if I connect capacitor in series, then the formula is given by 1 by C net is equal to 1 by C1 plus 1 by C2, so on. How many capacitors to have? I can write the formulas consistently, regularly, right? So these two we know already. So my third circuit element is inductor. So what will happen if I connect inductor in series? Okay, what will happen if I connect inductor in series? Then the formulas goes as of similar to resistance. Okay, therefore L net will be equal to L1 plus L2 plus L3, so on. No change. How do we have the resistance? We have same as induction. Okay, so they follow the same formula. You could derive it very quickly, very easily without a problem. Since the derivation is very, very simple, I'm going to skip the derivation. I hope it's not a problem, right? Yeah. So the inductor in series follow the same formula of resistance in series. Okay, cool, right? Okay, so moving ahead, so let me see what will happen. So you might have already guessed by now. So it will be same as that of resistance in parallel also. There is no change. Okay, for example, if I connect resistance in parallel, R parallel, 1 by R parallel will be equal to 1 by R1 plus 1 by R2, so on, right? Similarly, 1 by R inductance in parallel will be equal to 1 by L1 plus 1 by L2 and so on. There is no change here, right? So same as resistance in parallel. But for capacitors, resistance in capacitors in parallel will be equal to 1 by, so C1 plus C2 plus C3, so on. No change here, right? So hi, good afternoon, hello. Okay, cool. So this is how it moves on for the PAL connection. These are very pretty simple formula. Just I wanted to make sure you know them, so I've written them. Okay, cool, right? So there, I hope there is no problem with here. Once restart the app and try to rejoin. Sorry, Bhargav, I didn't get you, bro. What were you trying to say? Acha, you're not able to see my screen. Acha, I thought you're not able to see my video. Okay, okay. Yeah, bro. So what you do is you just quit the YouTube app and come back again. Okay, that will try. That will help you out. Cool. Or maybe the net is quite low. Okay, Radhika. Cool, cool. Sure. Yeah. Yes. Moving ahead. Okay, so later on, so let me start a concept for today. Completely a new concept is called generator. So our aim here it is to understand how the electricity is produced and how do we transfer from one place to another place. Okay, so we'll start with a very small experiment. Okay, cool, right? So which is, see, if I want to use electricity in my home, the electricity has to be produced at some point. So the first point is production of electricity. So we have to produce electricity at some point. Then from that particular point to my home, I have to transmit the electricity, transport or transmission of electricity, right? And third point is then when the electricity comes back to my home, I have to use it. So these are the three simple steps used in transmission of electricity. So we'll let us concentrate first on the production. So how do you produce electricity? So to produce electricity, we use something called as generators. So you might know this. When there is no electricity, we use a diesel generator, right? In your schools or in any like shops, we do use that, right? So we use generator to produce electricity, and for transmission, we use a very huge number of devices. Like we use transformers, we use cables, very high strong cable, right, which can carry heavy strong current, okay, which is like at high very voltage. We use transmission wires, and later on we also uh, use transformers. Okay, before we use the electricity, we use transformers, and we use our electrical appliances. For example, if I'm using a laptop, I have to charge my laptop, right? So I'll be using the appliances. So, and two important concepts here which we need to learn are, one is a generator, how do we produce electricity, and how do we transmit the electricity using transformers. Okay, so we're going to concentrate very much on these two for today's class. So what is a generator? What is a transformer? Okay, so as I already told you, we use generator to produce electricity, and I use transformer to transmit the electricity. Okay, it transform. What is transform? Convert from one form to another form, right? What is generation? To generate electricity. So that the name itself will give a very good idea, right? Generation, production, transform, converting from one form to another form. Okay, so remember that those two tricks here, and I'll explain you in a moment. Okay, cool. So let us now understand how to produce generate electricity using a generator. Okay, so we know that magnetic flux phi is equal to dA cos theta, right? So this is given as magnetic flux phi b, and whenever flux changes, for example, whenever there is change of flux, I know that EMF is induced. If EMF is induced, therefore there is current also in the circuit, right? So I need to change the EMF. If I want to induce EMF, I have to change the magnetic flux. So what are the three ways to induce the flux change? First way is to change the magnetic field. Magnetic field, you have to increase the magnetic field or you have to decrease the magnetic field. That is one way of producing current. Second way is shrink the coil. Shrink the coil or expand the coil. When you change the area, you get electric current, or change the angle, rotation. So when you change the angle, then you get electricity. And one of the most easiest way is to rotate. Okay, the most easiest way to generate is rotation, and all our electricity up to around 98% of electricity which we generate are used by rotation. I'm excluding petroleum and coal, right? So then what I get is almost all the energy what we generate is from rotation. Okay, so I'm excluding solar energy also here. So then how do we get electricity from rotation? The idea is very simple. Okay, the idea is very simple. So what happens is, for an example, take waterfalls, hydroelectricity. So water is falling from a very high waterfalls or a dam, and I'm placing a turbine here. I'm placing a turbine here. Okay. And on the turbine, I'm coiling the wire a lot. I'm coiling the copper wire very strongly, densely. There is thousands of copper coil around this turbine. Okay. And I'm going to place two magnetic fields here. Okay. One is the North Pole, other is the South Pole. So when I place a North Pole and the South Pole, what will happen? The magnetic field will be going from North Pole to South Pole, right? And whenever this coil rotates, so now the coil is like this, after some time the coil starts to rotate. Okay, the coil will become like this, then it will become flatter, then it's rotating. Okay, so imagine the coil is rotating in this particular axis. Okay, when the coil rotates, the angle changes, the theta change hoga. What happens? Va cos theta. When cos theta changes, there is change of flux. Whenever change of flux is happening, and EMF is induced. So this is the most basic principle of how we generate electricity. Okay, this is how we use to generate electricity. Okay, cool, right? So, so what I'm trying to say is, see the diagram here. There's a very good depiction of the generation of electricity in this diagram. Very clearly they are given. So what happening here is, see, there are two magnetic poles. One pole is here, okay, and the other magnetic pole is here. Very simple, right? And what's happening due to water falling on this turbine, this rod rotates here. Whenever this rod rotates, this rod has a lot of coil here. So when this coil rotates, when coil rotates, the theta changes. Whenever theta changes, flux is induced. That's a very simple idea. Okay. So what's the principle? The generator works. The generator works by changing the angle theta. So theta where is? So when theta where is, phi changes. When phi changes, EMF is induced. That's power generation. Okay. That's simple as that. So we can derive also the expression how much electricity we are generating and what kind of a current is it. Is it an alternating current or is it a DC current? We can also derive the formula with using very simple uh, derivations. Okay. So this is how it looks, guys. I'm writing a very simple diagram. This was the actual diagram here, engineering diagram, and I'm converted that into a block diagram here. So what's happening in the block diagram? In the block diagram, there's a north pole and a south pole, and in between have placed a magnetic coil, sorry, conducting coil. Okay, so there is two poles, North Pole and South Pole, and there's a copper coil. So there'll be n number of coils. Okay, there'll be not just one coil. There'll be very strong n number of coils. Okay, and what will be the direction of area? So area will be pointing upwards. Okay, initially, and for this particular case, when water falls on this and it start to rotate, the plane will change and the area vector will change. Right, it's rotating now. The area is changing. The direction of area is changing because it is rotating. So theta keeps changing continuously. Okay, so let me use Michael Faraday's formula, which is EMF induced is equal to minus d phi by dt. Right, so this is Michael Faraday's very simple formula, which we're seeing from the first chapter. So EMF is equal to minus d by dt of what is magnetic flux? Ba cos theta. Okay, and since there are n number of turns in the coil, I can put n also here. If I remember, right? So if there are very large number of coils, I can put n here. So it becomes n d phi by dt, and therefore EMF induced is equal to minus n dBA cos theta, and I'm differentiating with that with respect to time. If you notice, the magnetic field is not changing, the area of the loop is not changing, only the angle is changing, right? So I can bring B and A outside, therefore EMF induced is equal to minus NBA cos theta can be written as cos omega t. So d by dt of cos omega t. So this is the thing I need to differentiate. That's correct. That's correct, Radhika. Good. Okay. So this is the thing I need to differentiate. Why did I write theta is equal to omega t? Because if you remember the 11th concept of angular velocity omega is given by displacement by time, angular displacement by time. Therefore, theta can be written as omega into t. Right, very simple. So I'm just, instead of rating cos theta, I'm rating it as cos omega t, because this rod here, it is rotating with velocity omega, angular velocity omega. Okay, so I can just modify the formula in a very simple form, and this is what I get. Okay, so guys, can you tell me now what is the differentiation of cos omega t? Yep. So who can tell me? Yeah, so let me see who will answer me the very quickest. What is the differentiation of, okay, so let me ask you in a simple way. What's the differentiation of cos theta? If you can differentiate cos theta, then you can differentiate cos omega t also. That's correct, Rajama, but you're missing one term there. Radhika, correct. Good. Yeah. Vandita, correct. Suchindra, correct. Awesome. Very good, guys. So if you remember, guys, differentiation of cos theta with respect to d theta is equal to minus sin theta, right? So this is one of the basic formula which you learned from 11th, right? But here I don't have theta and theta, rather than have different forms. So how do they look? One is d by d of cos omega t with respect to dt. So t is the variable, t is the variable here. I have extra omega here. That's correct, Devakarani. Good. So I have extra omega here, right? So how do I do this? By using substitution rule. So what I can do, I'll do it very quick. So omega t, I'm just substituting it as u. Okay, I'll substitute omega t is equal to u, a random variable. Then I'll differentiate whole of this with respect to dt. Okay, d omega t is equal to du by dt. So omega is a constant velocity, so it comes outside. Omega into dt by dt is equal to du by dt hoga, right? So dt dt cancel ho jayega. Omega dt is equal to du. So I'll get this particular formula, right? Yeah. So or dt is equal to du by omega. I'll get this particular formula. So next, let me substitute here. So what is d by dt of cos omega t? Cos omega t is cos. So I don't need this, right? I think I just made complicated, but fine. Okay, we'll work it out. Not a problem, right? So then I'll write it as cos u. Very simple, because omega t is substituted as cos u, and dt can be substituted as du by omega. Right? I'll use this substitution. So d cos u as it is in the numerator, nothing changes. In denominator, dt is replaced by du by omega. Omega comes upside. Okay, therefore omega is equal to, what is du by cos u? Du by cos u is minus sine u. Okay, and what is minus sine u? Sine u is nothing but u. What is u? Omega t. Right? I hope you can do this very quickly in simplest forms. Not a problem. You can do however you need to do. So this is the differentiation what you get. Okay. So then let me substitute here. EMF is equal to minus CNBA. This becomes minus omega sine omega t. Okay, bas. Okay, EMF is equal to negative of negative becomes positive. Okay, then later on I get NBA omega sine omega t. So if you notice, guys, one very simple formula here is n is total number of coil, B is magnetic field, A is area, omega is velocity. They're all constant variables here. So I can substitute them as E naught, which is some number constant again, into sine omega t as it is. So this is the induced EMF, okay, in a generator. This is the amount of induced EMF in a generator. Bas. Oh yeah, cool, right? And last modification, you can modify this into one more simplest form, which is if I divide this whole expression by resistance R, both the sides. I can divide both the sides, right? It's not a problem. Nothing will change. Sine omega t. Okay, so what is E by R? Voltage by resistance is current I. E naught by R naught is I naught sine omega t. So this is the induced current in a generator. This much amount of current will be induced. Okay, and if you notice, the current I is a function of sine. So since the current is a function of sine, how does it vary? It varies as a sine function. Okay, so the current will vary in this particular way. The maximum value of this current will be equal to I naught, and the minimum value will be equal to minus I naught. Okay, yeah, so that's all. So this is a direct current or alternating current. This is an alternating current. So this is how do I get the alternating current in a generator. And this is, that's all, guys. There is no extra concept on generators. So generator completed, right? So I started with the most simplest formula, and I derived a formula for electricity generated using a generator. Am I clear, guys? If I'm clear, click on yes. So let me have a very quick recall of what I did here. Okay. So I start with Michael Faraday's formula of EMF. EMF is equal to minus d phi by dt. Since there are a number of turns, I'll multiply that by n. So and d phi is equal to ba cos theta. I substituted it. B and A are constant. I bring them outside. And cos theta I'm written as cos omega t. After this differentiation using basic differential calculus, what do I get? I get this differential as minus omega sine omega t, where omega is the angular velocity. Okay, cool, right? So after I getting minus and minus, I'll multiply. I'll get positive nba omega sine omega t, right? So n is a constant, b is a constant, a is a constant, omega is a constant. So constant multiplied into constant will always be a constant. I'm writing that constant as e naught. Okay, and sine omega t as it is. If I divide this whole equation by resistance R, I get current I is equal to I naught sine omega t. And this is an alternating current because it's a function of sine. Sine varies like a wave. Therefore, current also varies like a wave. And this is called as alternating current. From this point, I'm supposed to start a new chapter called AC current. But we'll see which chapter we're going to start. I'll tell you later. Okay. So am I clear, guys? Come on, respond quickly. Yes or no? So the derivation is very simple, right? Yeah, good, guys, awesome. Cool then. So if you have any doubt, let me know quite very quick. Okay, Nitank, okay, Anisha, good. So if you have any doubt, let me know very quickly so that I can respond to your doubt and move on to new concept of transformers. Okay, transformers. Cool, great, guys. YouTube guys, am I clear? Okay then. Cool, guys. So let me move on to transformers. So the first step of generation of electricity is over. Now I need to transform my electricity from one point to other point. So you might have noticed when you're walking in your near your home or when you're traveling, you might have noticed this instrument near the electrical poles, right? So this is called a transformer. And why do we need a transformer? There's a very good reason behind this, and there's a very big story also. Like okay, about a fight between Tesla and not Michael Faraday, Thomas Alva Edison. So there's an awesome story also. So what happened once was I'll tell you very quickly. So there was once a guy called Thomas Alva Edison, right? All of you know him. So this Thomas Alva Edison was the guy who invented electric bulb, right? And he used DC current to transfer current from one particular point to other particular point. For example, imagine he's staying in London. So from the one point in London to another home in London, he was using direct current for transmission. Okay. Then comes a guy called Nikola Tesla, who is a bit younger than Edison, and he is the father of alternating current. Okay, so he was the first guy who deduced alternating current, who was a very expert in producing alternating current, manufacturing alternating current. And he told that this is not a good way of transferring current, AC is a better way of transferring current. Okay, and then Edison told, no bro, I'll not do that, because DC was very costly at that time, because DC can't be transmitted for longer distance, only rich people had access to direct current. But Nikola Tesla thought that if I use alternating current, the transmission will be easy and it becomes cheaper. So everybody can get the electricity in their home. So Nikola Tesla thought that, okay. But there was a very big fight between Edison and Tesla, and Edison removed Tesla from job. He became jobless, but later on he succeeded. Okay, now all of us use alternating current itself, and finally Nikola Tesla won the battle also. Okay, so, and why is AC better? Why is not DC better? We'll come back to the AC current chapters, AC circuit chapter. Okay, but I'll tell you one important concept here. So the transmission was a very important concept here, because DC was very easy to transfer. Sorry, very difficult to transfer, but AC was very easy to transfer. Transmission of AC is easy. But what is this transmission? Why it is not easier? Why it is tough? Because see, now using a generator, I have produced electricity. There is a huge amount of electricity now, and I want to transfer electricity from, for example, near some waterfalls. I will produce some electricity near a waterfalls, and I want to transfer this electricity from waterfalls to house. Right. For example, if it is produced somewhere 300 kilometers away from me, how do I get 300 kilometers of current to travel from that point to this point? We know that the electricity will be dissipated in the form of heat. If there's a wire, if there's a cable, that cable will have resistance R. So if I send some current here, the current will be lost in the form of heat as I square RT, right? So I can't transform or transfer high amount of current, because the heat will be dissipated and everything will be lost. So if you send huge amount of current from the generation point, when it comes to your home, it will be very weak current. So they are facing a lot of problem. Okay, but one guy again, Tesla comes into picture and he devises transformer, and transformer plays a very important role. So what do they do is they're like magic boxes. Okay, they're like magic boxes for now. I'll tell you the detailed construction later on. So what does transformer do? So what does transformer do is it will convert this produced current into high voltage and a low current. It will increase the voltage and it will decrease the current. Okay, and later on here, always we use two transformers. Okay, one is to increase the voltage, other is to decrease the voltage. Okay, in the transmission line you always see these two kind of things, and now the current will be increased. Okay, why is transformer a magic box? Because we know that V is proportional, V is equal to IR. जब potential increase होगा, current also needs to increase, right? Both of them are directly proportional to each other. But transformer is a different kind of device which can increase the voltage, decrease the current, or it can do the reverse also. If it decrease the voltage, it can increase the current. Okay, so that is why we use transformers. So what does transformer do is very simple. There is huge amount of current flowing here initially, right? So what does it do is it will increase the voltage of the current to very high value, and it will decrease the current to very low value. जब current कम होगा, heat dissipated is also very less, right? So there is less when the current is very low in the circuit, heat dissipated is also very less. Okay, and we can transfer current from one point to another point with less amount of loss. Then before we using the electricity in your homes, again we use one more transformer, and now that will do the reverse. So what it has higher voltage, now it will decrease the voltage and it will increase the current. It will increase the current. Now we can use it safely without any problem. Cool, right? So I'll explain this again in detail, so no worry. Okay, can we keep the turbine? Of course, generator is the place we keep the turbine. Turbine is what rotates. Okay, the thing there. Cool. So did you get it, guys, or was it complicated? So I'll go step by step. Okay, so pay very careful attention. Okay, so yeah, so let me note it down step by step. Pay as much attention possible. Okay, so first step is transmission is difficult. Okay, transmission is very difficult because if current is high, okay, heat loss heat loss is also very high. So what I need to do to reduce the heat loss, I'll decrease the current. I have to decrease it very high, then heat loss will be reduced. Heat loss will be reduced. So how do I reduce the current? I reduce the current using transformers. I reduce using current transformers, so it is now good to transport, good for transport. Okay, but if current is very low, again I can't use it in home, right? So again I use the transformer and increase the current value to how much ever I want. Okay, so this is the basic principle of transformers. Okay, so don't worry, when we come to AC circuit chapters, I'll be explaining this in much more detail. But I'm trying to give you an idea how what happens. Okay, okay. So since okay, I'll give you an idea also. Have you when you're traveling in a railway station or when you see that transformer, they'll make a notice like this, right? So they'll put a very big skull here. Okay, after putting a big skull there, they'll put like this: high voltage, do not touch. 10,000 voltage or 1 lakh voltage, do not touch. Very dangerous. They'll put rise. They'll put this symbol, right? That is why what's happening here. So they have transformed this voltage to very high voltage. There'll be thousands and like I mean like tens of thousands of voltage. If you touch it, it'll be dead in a moment. It'll be dead in a moment, right? So it'll be very high. That's correct, bro. Yeah. So I hope you have noticed this. Okay. So that is why to touch the wires is very dangerous. Okay. In your home, the voltage will be less. So let me draw one. If you want, you can take a screenshot of this, guys. Okay. If you want, you can take the screenshot of this also. So what happens is I'll draw a very short screen diagram now. Okay. Pay attention, which is at the point of generation, the voltage is low. Okay. When I put a transformer, voltage will be very high. Okay, then that high voltage current will be can be transferred very easily without any problem. Then you can't use that high voltage current. Again, I use one more transformer and reduce the voltage. Then I'll use it to home. So this is the voltage diagram. Okay, so this is the point of generation. This is the house, and here the voltage is. This is the graph of voltage. This is the graph of voltage. There is low voltage, but then in the transmission wires where you see in the road or near the railway station or the substation, they have high voltage, like tens of thousands of volt. The point where we increase the voltage, the transformer what we use to increase the voltage is called as step up transformer. Okay, it is called as step up transformer because voltage I'm increasing, right? I'm upping the voltage. It's called as step up transformer. And the place near my home, okay, near my home, there will be one more transformer in the electric pole that will reduce this voltage to lower voltage, and that is called a step down. Oh, why I'm writing a city always? Step down transformer. Cool, right? Yeah. That should we be afraid of high voltage current or high currents? Both of them are dangerous. Okay, even a milliampere of current, which if it passes through your heart, okay, this is not a good shape of heart, but think this is a heart. Okay, and I was trying to do. Okay, so there are a lot of aorta, superior vena cava, inferior vena cava. There are a lot of heart, and how does this work? A small electric pulse in the heart. Usually, you know, in lot of places in our body, alternating current is generated. How am I speaking? When I'm speaking, right, there are neurons travel. There are signals traveling in my neuron in the form of alternating current. How is my heart beating? Like how is my heart pulsating? Right, that's also in the form of alternating current. So my heart usually work on alternating current. Okay, generated inside my body. If I pass a milliampere of current to my heart, it can die very quickly. So even a small current can kill you. Okay, if it passes through your heart. Okay, and even the small voltage can also kill you. So everything is dangerous, but how do they act is very important, because if you just touch a very high current and if it doesn't form a loop, for example, you are standing on a rubber mat. Okay, you are standing on the rubber mat. Okay, so wait, guys, let me ask a very simple question. Okay, this is out of topic. Okay, this is not included in the chapter, but I'll ask you a simple question. So imagine there are two, three electrical lines passing from one pole to other pole. If I touch this pole, I'll burn, I'll die at the moment, no doubt. Okay, if I touch this electrical wire, is carrying a huge amount of current, I'll die at the moment, at the spot. But a bird can stand on the wire. I mean, right? The bird won't die. Can you tell me why, guys? The bird won't die. The bird will be happy. I mean, it can sit for many times, then it will fly back. Yes, Rajesh, can you tell me why? Anybody? I mean, you raised your hand, so I thought you know the answer, bro. So can you tell me why the bird won't die? Food is insulator. Okay, but there are few birds who get electrocuted also. Not right. That's correct. That's very good. Okay, bird dies in front of my home because the why both legs are exactly in front. That's good. So what's happening here is, see, when I'm starting on the ground, the electricity will pass from the wire. Okay, it's forming complete loop. The electricity will form completely travel from the wire to my hand, through my body to the ground. So it's completing a circuit. Whenever water comes in contact with my body, again heat is generated, and that heat will burn me. Okay, that heat will burn me because every human body has good amount of resistance. They'll burn and will die. Okay, but notice bird is not making complete circuit. So bird, both the legs are in same potential, because see, my leg is at low potential, I'm on ground, and my hand is at high potential, so current will flow from high potential to low potential. But if you notice, both the legs of the bird are in the same potential, so there is no delta V, there is no potential difference, and the complete circuit is also not formed, just like here. So the bird will not die. For example, if the bird touches this wire by mistake, then it will form a complete loop, it will die. Okay, so forming a complete loop is important here. Circuit is not completed, current is not passing through the bird's body, there is no potential difference. Very good, guys. Awesome. All of you right. Cool. Great. Right. So which type of current is produced in turbine, solar, AC or DC? Bro, it is AC, bro. See, we derived the formula here, right? So if you are hanging, then we are safe, bro. Right. If you are hanging, we are safe. Okay. So see, this is a way we always generate in generators alternating current. Okay, that is why if somebody is trying to repair some Bescom or electric wires, they use rubber gloves, or they use very strong rubber boots, right? So to not to complete the circuit, they'll try to remain safe. Okay, okay. So coming back to, I'll come back to the chapter now. Okay, so we'll try to discuss how does it work and what is the principle of transformers. So let me write to 2 3 points which are very important. Transmission is difficult. Transmission is difficult. Okay, because of high current. If current is high, dissipation, heat loss is also high. So I use transformers to reduce current. I want to reduce current, I use transformers. Okay, then I can transfer it very easily. When current is low, transferring is very easy. Then again, to use it in my home, I can increase the current. Again, I use transformers. Okay, so this is the basic principle. So transformation is very tough. So I use transformer to reduce the current and increase the voltage. And again, I use transformer to revert it back to the original condition. Cool, right? And that is the formula here. Cool. Okay, guys. So if I cut this transformer, if I take the transfer section here, is it called the longitudinal section? I'm not sure about biology, but if I cut this particular transformer, okay, I'll have this kind of structure. So there is current coming from the big cable to the transformer, okay, and it is coiled and it goes back out. And whenever current is moving here, what happens? The magnetic field is created, right? The magnetic field is created here in this coil, and this magnetic field will induce current here in this coil, and bulb will switch on, or we can use that current in our homes. That is a very, very simple ideology, what we have seen in mutual inductance also, right? So what's happening is very simple. There are two kinds of coil. One is called primary coil, other is called the secondary coil. So primary coil is the input, secondary coil is the output. Okay, cool, right? So the very high current is passing through the primary coil, then it goes back outside. When the current is passing through this coil, a magnetic field is generated, and that magnetic field can generate current in the secondary coil. So primary coil is P, IP is primary current is IP, secondary current is IS. So this is called secondary coil. Okay, P is for primary, S is for secondary. So this is primary current IP, primary voltage VP, number of turns NP. Primary coil. Secondary coil has secondary current IS, secondary voltage VS, secondary number of turns NS. Cool, right? So how does it work? Okay, guys. So it's very simple. Pay attention here. What's going to happen is whenever current is flowing in this circuit, there is self-induction. There is self-induction in this coil, right? Because of the current, this coil will try to oppose the change in current, and self-induction is happening here. And later on, due to the magnetic field linked with this coil, mutual induction is also happening here. So both of them are happening, right? So there is self-induction and mutual induction also happening together. Okay, and notice magnetic flux is same for both of them. Flux is same for both of them. Same field is related to both the fields, right? So let me write the equation in the first case. So in the first case, what's happening? Self-induction, ES, sorry, E primary, right? In primary coil, there is self-induction. So EP is equal to number of turns in primary coil minus d phi by dt. Wait, so let me write this very clearly. Okay, so in primary coil, there is self-induction. In primary, there is self-induction. So what happens to self-induction? We'll write the formula for self-induction. Okay, so self-induction EMF E1 or E primary is equal to self-induction is how much? L, right? Self-induction is LP in primary coil and d phi by dt or di by dt, right? So di by dt. Very simple. So this is self-induction in the primary coil. And in the secondary coil, I similarly have mutual induction in secondary coil. In secondary coil, what should the mutual induction? E of secondary coil will be equal to, it is due to mutual induction, so I'm writing mutual induction in secondary coil, and current will be di by dt. Current will be di. Do you remember this formula, guys? So we learned this formula already, right? So EMF is equal to minus d phi by dt into N, or EMF is equal to minus L di by dt. This is in the form of self-induction and mutual inductions. So I've written these two formulas. Now I'll divide these two formulas. Okay, current is same. Okay, current is same. To convert, because power input is equal to power output. If I put power input is equal to power output, I have to maintain same current. Or we'll make a small assumption that current is same for some moment. Okay, so that's a very small assumption here. I'll divide both of them. Okay. So EP by ES is equal to minus of LP di by dt minus of MS mutual inductions di by dt. So di by dt cancel हो जाएगा. I'm left with EP by ES is equal to minus minus b cancel हो जाएगा LP by NS. So what is LP, guys? LP is self-induction. So let me write the self-induction formula. What is the self-induction formula here? So N mu naught A by L. So let me write the formula here, which you already derived here. So primary is number of turns in primary coil square area mu naught by length L divided by what is the number of turns in secondary coil due to mutual inductions, N1 into N2 into area into mu naught by L. So A mu naught by L cancel हो जाएगा, A mu naught by L cancel हो जाएगा, N1P cancel हो जाएगा, NP1 cancel हो जाएगा. I'm left with NP by NS. So the most simple formula here is EP by ES is equal to NP by NS. So this is the formula for transformer, guys. So this is the whole formula for transformers. Again, the derivation is not much more important, but try to remember the derivation also. Okay, so let me do the derivation again once more so that everybody will be clear. Cool. So give me 2 minutes, guys. That's all. I'll finish it up here. So there is primary coil, there is secondary coil. In primary coil, there is self-inductance. In secondary coil, there is mutual inductance. So I can write the formula: E primary is equal to minus of self-inductance L primary into di by dt, and similarly E secondary is equal to mutual inductance in a secondary coil into di by dt. When I divide both of them now, minus minus cancel हो जाएगा, di by dt cancel हो जाएगा. I'm making a small assumption that di is same amount of current is induced in both the coils. So I get the formula, which is EP by ES is equal to LP by MS. What is mutual inductance? Mutual inductance in primary coil is N primary square mu naught A by L divided by what is mutual inductance in secondary coil. So NP into NS into mu naught A by L. So mu naught A by L, mu naught A by L cancel हो जाएगा. One NP and one NP cancelled out. So what I'm left with? I'm left with EP by ES is equal to NP by NS. Okay, that's all. So this is the formula for transformers. Cool, right? I hope you're clear with this, guys. Very simple formula. Try to remember. Again, derivation is not important. Nobody is going to ask you for the derivation, but I should not just tell you the derivation, right? So I'm just giving you the formula. Acha, okay, good. Actually, I'll come back to that doubt in a moment. Okay, wait for some time now. Cool. Am I clear, guys? Am I clear with this formula? So click on yes if I'm clear with this formula. Or simply, if you remember meter bridge, E1 by E2 is equal to L1 by L2, right? Same here. E1 by E2 is equal to N1 by N2. So this was for potentiometer and meter bridge. But similarly, same formula I have here. E1 by ES, E1 by E2 is equal to N1 by N2. Am I clear, guys? Click on yes or no if I'm clear. Quick. Oh, okay. Good, guys. Good. So very simple. Just dividing the formula will give you the answer. Okay. So now I can tell you the step up transform and step down transform. How can I increase the voltage and how can I decrease the voltage very easily. For example, take E2 by E1 is equal to N2 by N1. You can use P or S or 1 or 2 or anything, whichever is comfortable to you. Okay. So E2 by E1 is equal to N2 by N1. Or very simply, I can write E is directly proportional to N. EMF is proportional to number of turns. Okay. So how does a step-up transformer looks like? So step-up transformer, the number of turns in secondary coil will be greater than number of turns in primary coil. See, the red, there are more number of turns compared to the green number of turns. So here it is input, here it is output. So output has more number of coils. Since E is directly proportional to N, therefore EMF2 will be greater than EMF1. So this is called step-up transformer. It will have high voltage when compared to the initial voltage. Imagine a 6 or 20 kilovolt current is coming inside, but when it's going outside, it can be 410 kilovolt. So depending on the number of turns, I can increase the voltage to very high values. Okay. Similarly, step-down transformer also works on the same principle. I have a number of turns N1 here and number of turns N2. Here I have N1 greater than N2. Right, N1 has more number of coils, therefore E1 will be greater than E2. So initially, the current here will be flowing will be 410 kilovolt, but when it comes outside, it will be just having 20 kilovolt. It is stepped down now, right? The voltage is decreasing because number of coil decreases. So the answer is very simple, guys. The induced EMF is directly proportional to number of coil. So step up coil will have high number of turns in secondary output, secondary coil, and step down transformer will have least number of coil in the secondary winding. Yeah, depends on coil. That's correct, Radhika. Yeah, so depends on number of turns of the coil. Very simple, right? So EMF is directly proportional to number of coil. So which among these two, which has highest number of coils, will have highest EMF. That's all. Okay. So initially I got less number of input, less number of coils. So output I have more number of coils. So I'll have more EMF. So that is called step up. Voltage will increase. Okay, exactly opposite in step down. Number of coils will reduce in the secondary coil. Voltage also will reduce in the secondary coil. Okay, am I clear now? So if step down and step up are clear, click on yes, guys. Click on yes or no if I'm clear with step up and step down. Quick. If you have any doubts, text me. Okay. YouTube guys, am I clear? Zoom guys, respond with yes or no. Okay, cool guys. So by this, the chapter is completed. Okay. So the last concept of this chapter was transformers. So I've completed transformers as a generator, and this is the end of the chapter. Okay. Okay. So later on, what we can do is we'll have a very quick recall of all the concept of this formula in 5 minutes, and rest 40 minutes we'll spend time to solve the problems. Okay. Cool, right? Which are very important for exam. Like I'll be solving very high probable exams, questions which are highly probable in exam. Okay. Cool. Awesome, guys. Thank you from YouTube and Zoom for responding very quickly. Okay. So let us recall very quickly. Okay. So we'll start from EMF, right? Magnetic flux. So we know in the first concept of this chapter, we studied something called as magnetic flux. So what is magnetic flux? If you remember, guys, magnetic flux is the number of field lines passing through a given area, and that was given by phi B is equal to B dot A or BA cos theta or BA cos theta. So this was the magnetic flux which we already studied in the first chapter. And whenever any one of this variable, either B or A or theta changes, flux changes, and whenever there is change in flux, an EMF is induced. And this was done by Faraday's experiment. Faraday did this experiment many times and gave us a Faraday's law, which was induced EMF is equal to minus d phi by dt. The rate of change of flux is equal to the EMF induced. Okay, cool, right? So this was the Michael Faraday's law of induced EMF. So later on, after some 15 years, a person called Lenz comes into action, and he tells this why there's a negative sign here and what is the meaning of the negative sign. Okay, he tells that I get a negative sign here because of the opposition. Like inertia, like when you have a very big object, it's very difficult to move, right? Similarly, when there is current, it is very difficult to increase or decrease the current also because of opposition from the circuit. Okay, and that is why we have a negative sign, right? And later on we went and we saw how a north pole or a south pole is created in the loop. For example, if I have a loop here and if I put a magnet into the loop, north pole and south pole, if I'm inserting it, I get a north pole here to oppose. They repel now and it is opposition, right? So we know that how a north pole is created and how a south pole is created. Whenever a north pole is created, can you tell me the direction of current, guys? What is the direction of north pole current and what is the direction of south pole current? Yeah, that's correct. So if I have n number of turns, I have to multiply this whole term by n also. That's correct. Yeah. If there is one number of turns, I won't multiply. If there are n number of turns, I do multiply it by n. Okay. So can you tell me what is the direction of current when north pole is induced? If I get a north pole in this coil, what will be the direction of current, guys? Exactly. Good. So how do we do this? Exactly. So you put two arrow marks at the top of the north, right? When you put two arrow marks, you can notice that it is going in anti-clockwise direction. The current is moving in anti-clockwise direction. Very simple, right? And the current in south pole, whenever south pole is induced, the direction of current is given by again putting the arrow mark at the end of the south yes alphabet. I get clockwise direction. I get clockwise current. That's correct. Good, guys. Awesome. So you do remember. Awesome. Cool. So this is up to Lenz's law what we saw, right? So later on, after we finished Lenz's law, and we went to study motional EMF, right? So what was motional EMF? So motional EMF is a very simple and amazing concept. So whenever there's a metallic conductor placed in a magnetic field, okay, and if I move this metallic conductor with velocity v and it has some length L, then the induced EMF E was equal to BLV, and this was called a motional EMF because it is due to motion, right? So this was called the motional EMF. Similarly, we also understood rotational EMF. So I take a rod, okay, a metallic conductor, and I rotate it with the angular velocity omega, then the EMF induced is equal to half B omega square L. So B omega L square. So this is called the rotational EMF. Rotational EMF. Right. So induced this is motional EMF because of linear velocity and rotational EMF because of angular velocity omega. So we saw these two also. We derived the formula for both of them, right? Later on, we went and saw EMF due to induction. So EMF due to induction, and there are two kinds of induction, right? One is self-induction, other is mutual induction. The formula for self-induction is E is equal to minus L di by dt, and the formula for mutual induction is EMF is equal to minus M di by dt. So all the formulas in this chapter, okay, where you say EMF is written on the screen. Okay, so I've written the Michael Faraday's EMF formula, motional EMF, rotational EMF, inductional EMF. So all the formulas for EMF are written here. If time permits, or if there is a necessary situation, we can equate one of them, any other. For example, I can equate this EMF to this EMF, or I can equate this EMF to this EMF. Okay, I can equate any one of them because all of the EMFs are same. Okay, so you can recombine them and make any number of formulas you want to make the formulas. Okay, cool it. But the situation should be in that particular way. You just don't simply combine. If the situation is in such a way you need to combine, you can combine them. Cool, right? So any doubts from this slide? Any doubts? Anything I need to tell or anything I need to recall? If nothing, then click on yes. If there is something, type what you want to know. Okay, type your doubt. YouTube guys, am I clear? Zoom guys? If everything is clear from this slide, click on yes. Lenz's law. Okay, so what happens with Lenz's law is, for example, imagine. So let me recall it very quickly. Okay, so imagine I have a coil here and I'm inserting a magnet into the coil. A north pole is being inserted, a south pole is being inserted. Okay, when I'm inserting a north pole into this coil, what's happening? The flux is increasing in the coil. When the flux is increasing the coil, what will happen? This coil will try to oppose the increase in flux. So what we'll do is it will create a north pole here. The current flowing will be in such a way that the current will create a north pole, north magnetic field. Now both of them oppose each other. North and north repel each other, right? So now this is the opposition set by Lenz's law. Okay, now they're opposing each other. So when North Pole is coming, that means the direction of current is anti-clockwise. How do I know that? Because North Pole I'll put arrow mark here, and North Pole I put arrow mark here. So that means the current is moving in this particular direction. It is moving in anti-clockwise direction. Cool, right? And in the next case, okay, so this is how it happens. Or in the next case, if I take South Pole here and North Pole here, and if I take the magnet outside, if I'm taking it outside, the field will be decreasing. The field decrease over a high. What will this current do? The current will try to attract. Again, it has to oppose the change, right? So decrease over a high, it has to oppose and increase now. So it will try to attract. While attracting, it will create South Pole here. Okay, so that the current will be flowing in clockwise direction. Cool. That is what Lenz's law is. If area changes, motional EMF will not change. Uh, so when see motional EMF is equal to BLV. So this is called a motional EMF. Okay, cool, right? And if area changes, of course EMF will change because EMF is equal to d by dt of BA cos theta, right? It is not called as motional EMF. That's all, Anusha. Yeah, of course, when the area increases, the EMF will be induced, but the increase of EMF due to change in area is not called as motional EMF. This is called a motional EMF. This is just the regular EMF. Cool, right? Yeah. Okay. Okay. I hope both of you are clear, right? Okay, cool then. So this is all the formulas and this is all the types of different kinds of EMF what I've written here. Cool, right? So next, later on, using this induced EMF, what was induced EMF? Induced EMF is equal to BLV. And what is induced current? Induced current is equal to potential by resistance. So induced EMF is BLV divided by resistance. So this was the induced current, right? So if I know the induced current, I can also write the induced power. Power dissipated is equal to EMF into current, or EMF square by R, or I square into how much? R. So these were all the different formulas of power dissipated. I'll expand this formula. What is EMF? EMF is B square L square V square. Right? I'm squaring the EMF divided by resistance. So this is the power dissipated in an inductor or in a rod carrying current I. Right? So this is the power dissipation due to this amount of current. And we know that power is equal to force into velocity, or force is equal to power by velocity. So this formula, and we also saw many problems on this formula, right? So this is related to motional EMF. Cool, guys? Yeah. So later on, we went and move on to generator. In generator, we got the induced EMF as E naught is equal to, sorry, E is equal to E naught sine omega t, E naught sine omega t, and the induced current is equal to I into I naught sine omega t. So, and it was a AC current. So what we get in generator was a pure AC current, right? And later on, we saw transformers. In transformers, we noticed that current induced in secondary coil by current induced in primary coil is equal to number of turns in secondary by number of turns in primary, or EMF is directly proportional to number of coil. So by this idea, I devised step-up transformer to increase the voltage, and by this idea, I devised a step-down transformer to decrease the voltage. Right? So generator भी हो गया, EMF भी हो गया, and motional EMF का भी लिख लिया यहाँ, right? And what I'm left with? Am I leaving anything? Okay. So I'm just the last formulas which you read to remember is self-induction. Self-induction L is equal to N square mu naught A by L, and mutual inductance M is equal to N1 N2 mu naught A by L. So this is self-induction and this is mutual inductance. Bas. Okay. I hope I covered all the topics just in 3 slides here. But I've written only the formulas, not all the ideas and concepts, but I hope you remember them and I hope you revise them. Okay, so I'll share you the notes. Okay, in yesterday I shared you, right, the Avanti module and motion materials. You can go through them. Motion is for advanced. Avanti, you can follow Avanti for mains. Okay, and you can follow the motion material which I sent you in the group for advanced. Cool, right? There'll be some few extra concepts here also. Okay, so what happens in self-induction mutual induction is, let me tell you very quickly. So whenever there's a regular coil, nothing happens. The current will go on as it is. But if I turn this coil and rotate them in this particular way, then this coiled shape will try to oppose the current. Okay, by inducing a induced current here, will try to oppose. And this opposition is called as induced self-induction, because it's happening in the same coil. some very big current is flowing in this direction, and this coil will try to oppose the direct flow of current, and this is called a self-induction. Okay, and similarly we have mutual inductance, which is if I take two different coils. Okay, I take two different coils now, and current is flowing in this coil. When current flows in this coil, there is a magnetic flux change, right? Magnetic field also it changes. Whenever current changes, magnetic flux changes. Due to change in magnetic flux, there's a current induced in this coil. Current is induced in this coil. Whenever current is induced, the opposition created here is called as mutual induction. It is called as mutual induction. Cool, right? So that's very simple idea about mutual induction and self induction. Cool. Okay, guys. So any doubts, guys? You want me to recall anything or repeat anything? If nothing, then we'll move on to problems. Okay, like very important problems which we are going to see in exams. And we'll see some one or two simple problems also. Cool. Okay. Cool then. If you have any doubts, you don't forget to text me, right? You can text me right now. Not a problem. Cool. Feel free to text. Okay. So coming back to the first question after the revision. So what will be the first question here? So let us read the question very clearly, understand it, then remember the concept. Okay. The first question here is a coil of 100 tons. So I have a coil here which has lot of tons. A number of tons is 100. N is equal to 100 here. Completely fine. And a current of 5 ampere is flowing in this coil, and the flux when the current of 5 ampere is flowing, it creates a flux of 10 raised to minus 5 Tesla meter square. Okay, so that much it creates per number of turn. This much amount of field is created. Okay, so later on they're asking me what is the value of inductance. So if a current of 5 ampere is flowing, and if it is creating 10 raised to minus 5 amount of flux, and if there are 100 number of coil, okay, so what will be the inductance? So guys, can you tell me how to do this? And self-induction magnetic flux is not changed. Of course it will change, Nama, when current is increasing. So you see, whenever you switch on the current, if there is no current, initially it will be 0 ampere. As soon as you switch on the current, it becomes 3 ampere, right? It is see, the current is increasing step by step. Whenever the current is increasing slowly, the magnetic field also increases slowly. So there is change in magnetic field here also. Flux यहाँ भी change हो रहा है, flux यहाँ भी change हो रहा है. Okay, how can I find out the self induction? So if you notice very carefully, I need to combine two formulas here, because N and phi are related by Michael Faraday's formula, and L and I current are denoted by induction formula. So what I do is I combine two formulas here. One is EMF is equal to minus N d phi by dt. Cool, simple. And one more formula is EMF is equal to minus L di by dt. Why I'm putting L is because it's only one coil and self-induction happens, right? So that's why I'm putting L di by dt. See, both of them are EMF, so I'll combine both of them. So when I combine both of them, a very amazing thing happens. So negative negative cancel, positive ho jayega. dt dt cancel, they cancel out. What I'm left with is N d phi is equal to L di. If I integrate di and d phi, dt cancel ho jayega. N phi is equal to Li. So I get a one more awesome different formula. N phi is equal to Li, right? N phi is equal to Li. So then what happens is, I want L, right? Therefore L is equal to N phi by I. So what is N? N is number of turns is 100. What is phi? Phi is 10 raised to minus 5. What is current I? Current is 5 amperes. Therefore L is equal to 5 ones, 5 20s. So 2 into 10 raised to minus 4 units, or Henry. Henry is the unit. Okay. So this is a self-induction, what I'm getting here. So I'll tell you once again what's going to happen here. So if you notice here, if you come back to this concept here and notice, the EMF induced is given by two different formulas. See, EMF is equal to N d phi by dt, and EMF is equal to here, if you notice, it is given by L di by dt. Both of them are same EMF, right? Both of them are exactly same EMF. So you can combine them, both of them. Combine both of them. So when you combine both of them, negative negative cancel हो जाएगा, dt dt cancel हो जाएगा, N d phi is equal to L di. So you can equate both of them because both of them are EMF formulas. Okay, so that's what I'm doing here. So I'll take those two different formulas. EMF induced by flux change is equal to minus N d phi by dt. EMF induced due to current change is equal to minus L di by dt. So equate both of them because they are EMFs. Yeah, cool. That's correct, Devakarani. Good, good, awesome. Yeah, cool, guys. So this is how we solve. Okay, it should be very creative in solving the problems. Okay, just don't stick to. If I just have written the formula page here, just that doesn't mean you have to use only those formulas. You have to be very smart. Okay, and understand the situation, what's happening. Okay, if you are very good enough in modifying the formulas, and most of the problems will become easier to you. Okay, they become way much easier to you also. Cool, right? Okay, so am I clear, guys? Click on yes if I'm clear. Okay, Jyoti. Jyoti, aren't you 11th student? Just, I don't know. I thought I saw you in 11th class. Okay, cool, not a problem. Okay, so moving ahead later here. Okay, so what's happening here is, let us try to understand what's going to happen in this question. Okay, so first step is to understand the question very clearly. Two coaxial solenoids. So I have two solenoids. So one solenoid is here, then there's one more solenoid here. Coaxial means they're the same axis. They're the same axis. No problem. Cool. Are made by winding thin insulated wire over a pipe of cross section area. So both of them have the cross section area of 10 centimeter square. Completely fine. Both of their length is 20 centimeter. Both of their length is 20 centimeter. Okay, if one of the solenoid has 300 tons, so this has 300 tons, this has 400 tons. What is that mutual inductance? And mu naught is given here. So they're asking what is mutual inductance, and it's a very simple formula. Mutual inductance is very simple. N1 into N2 into mu naught into area divided by length L. So number of turns is 300 in one coil. In other coil it is 400. Mu naught is given as 4 pi into 10 raised to minus 7. Area is given as 10 into 10 raised to minus 4 meter square. I'm converting this into meter square, right? So later on dividing by the length 20 centimeter. So that is 20 to 10 raised to minus 2. If you just multiply and divide, you'll get the answer. Cool, right? So this was one of the most simplest formula here. I hope this is very easy and clear, right? So they're given a lot of formulas here, just combine them, solve it, you'll get the answer. Cool. I mean, this was not an important formula, but anyhow, I told it here. It's a very simple question. Okay. Cool. So very, very important question, guys. So these kind of questions always appear in the exam, okay? If the coils have different areas and length, usually no Gunashri. Okay, if they have different area and length, we have to change the formula accordingly. Okay, because if you remember the formula, if you know the accurate derivation now, so I'll write the most accurate formula. Okay, if they have different length, use this formula. Mutual inductance is equal to N1 into N2 into area of coil 1 divided into mu naught divided by of L1 if current is flowing in coil 1. If current is flowing in coil 1, use A1 and L1. If current is flowing in coil 2, then use N1 into N2 into area of 2 mu naught by length of 2. So if current is flowing in coil 2. Okay, if you remember the derivation, that is how we have solved the problem, right? And this is how it looks if you have a different length. If they have the same length, just write A by L, or you have to include A and L in which the current is flowing. Okay, remember that. Okay, that's a good question. Like it. Cool. Okay then. So coming to one more important question here. Okay, which is in the given circuit. So notice here very carefully. So in the given circuit of resistance 2 ohms, there's a resistance here of 2 ohms at a certain instant, at a certain time. I don't know what time, but at certain time, the difference between A and B, the potential difference between this point and this point is 0.5 volts. The potential difference between these 2 points is 0.5 volts. Completely fine. Okay, and at that particular time, current is 0.5 amperes. The current flowing in this direction is 0.5 amperes, and di by dt, and the current is growing with respect to time. The current is increasing at 8 ampere per second. For every 1 second, 8 ampere of current is increasing. Okay. Then can you tell me what is the inductance of the coil? That's the question here. Very simple question. Okay, so pay very careful attention. If you know this, I hope Pradeep sir have taught you this. I'll tell you what is the basic concept what are going to use here. So if I have such instruments here, if I have particularly such kind of an instrument, have a resistance of 2 ohms and have an EMF of 8 volt, and if current of 1 ampere is flowing here, and this is point A and this is point B. For example, imagine this kind of situation. Then how do I draw the potential difference? So the formula how do I write is, at this particular point potential is VA. Okay, cool. And as I move on towards the resistor, as I move on towards the resistor, what will happen as I move along the direction of resistor? When my direction and current directions are same, the potential will drop at resistor, so minus VR. Okay, cool. Then after resistance, I'm moving towards the battery. So there is positive terminal, there is negative terminal. When I move from positive terminal to negative terminal, what will happen? The potential will again drop. So there is potential drop at battery at EMF, so at negative VE. And as soon as I pass the battery, what I'm left with? I'm just left with point VB. So this is how I read the formula. Okay, so this is called the potential drop in a circuit line. In a circuit line. So this is how we draw it. So I hope Pradeep sir has taught you this. Okay, this was one of the always mostly used concept. Okay, cool, right? So pay attention to this and remember about this. Don't forget anytime. Always try to remember this formula. Okay, I'm clear, guys. Did you get how did I do this? Click on yes if I have understood. How did I write this? Okay. Acha, good, very good, guys. Awesome. So same thing I'm going to do it here. Okay, same thing I'm going to do it here. But before doing that, I'll ask you one more question, one more simple question here, which is, see, current is increasing. When current is increasing in this coil, what will this inductor do? It will try to oppose the increase, right? So if it's trying to oppose the increase, what will it do? It will send a small current in opposite direction. Am I right? The current is increasing because di by dt is positive 8. There is 8 ampere per second. That means it is increasing 8. So the current in the coil is increasing. If the current in the coil is increasing, what will it do? This whole coil will try to decrease the current. By according to Lenz's law, it will try to decrease the current. So what I'm going to do is, instead of inductor, I'll write inductor in this particular direction because current is flowing, right? So I'll write in this direction. So now I modify the circuit, point A as it is, resistor as it is. Instead of inductor, I'm writing inductor in this particular shape, and point B here. So A, resistor, inductor, point B. Cool, right? Am I clear what I'm doing here? Okay, so since a very important point is the current is increasing. Whenever the current is increasing, that inductor will try to decrease the current. How does it decrease? If the initial current is flowing towards this direction, the induced current will flow in the opposite direction. Opposition, right? It has to oppose the increase. So they flow in opposite direction. Now they're cancelling. If the current is flowing towards left, that means positive terminal is towards left. So then I've modified the circuit here. Now I'll write the circuit voltage. So potential at A, okay, potential at A, because positive terminal, current always flows from positive terminal, current always comes out of positive terminal. So first I found a direction of current. The original current was flowing towards the right, the opposition current will flow towards left. If current is flowing towards left, that means positive terminal is towards left, because current always comes out of positive terminal. Oh. So give me a second, guys. The screen got off. So let me switch it on. Okay, cool, right? So then you can solve the circuit without any problem. Very easily, you can solve it out. You start from point A, go slowly. Okay, so give me a second, guys. I'm opening the PPT again. But the bad thing is nothing is saved. All of them are gone, but not a problem. Share screen. Only few problems left today. We'll wind up very soon. Okay, not a problem. So this is how I'm writing the circuit. I'm modifying the circuit. Hope you can see the screen now. Yeah. Okay. So now you can see the screen. Resistor is as it is. EMF is in this particular shape. Okay. Cool. And the current is flowing in this direction. Cool. Positive terminal is here. Negative terminal is here. So now let us draw the circuit voltage, guys, step by step. So let me draw the circuit voltage from one point. So here the circuit voltage is VA and here it is VB. So I start from VA. As I move along the direction of current, current will be lost. So potential will be lost. So minus VR. And as I move towards right side slowly, what happens is positive. If I go from positive to negative, again potential will drop. So potential will drop at inductor minus VL. And what is left is point B. Therefore, it is equal to potential at point B. Okay, so I'll modify this. VA minus VB minus VR is equal to VL. I brought VL to the right hand side and VB to the left hand side. What is VA minus VB? Given the question, it is 0.5 volt. So it's 0.5 volt minus what is potential drop at resistor? VR is equal to I into R. The current is 0.2, sorry 0.5. The current resistance is 0.5. So if I multiply this, I get 0.1. So therefore, EMF drop at resistance is 0.1 is equal to what is VL? VL is equal to L di by dt. L into di by dt. Right? Potential at inductor is L di by dt. Right? So use that formula. So you get 0.4 is equal to L di by dt is 8. So you divide this, you get the inductance. Okay, that's all, guys. This is how we solve the problem. Okay, and this question has a very high probability of appearing in your exams. Okay, cool, right? So hope I'm clear. That's correct. That's good. Cool. Am I clear, guys? So very simple. If the current is decreasing, see current was increasing in the circuit initially. Current was increasing, so the inductor will try to oppose the current. So they're coming in opposite direction. So that is why I'm writing polarity in this direction. Wherever the current is flowing, that direction will have positive terminal. So then I write the circuit voltage equation. Just plug into the formulas V is equal to IR, VL is equal to L di by dt. You'll get the answer very easily. So am I clear, YouTube guys? Zoom guys, am I clear? Respond with yes or no. Yeah, cool then. Good, awesome, great guys. Okay, if I have any doubt, let me know very quickly, right? Okay, awesome. Okay, so one more very key concept in solving problems is this one. Okay, so which is, if you, I hope you remember RC charging and discharging. Okay, so our resistance and our capacitor, then the current in the capacitor is given as I naught into e raised to minus t by RC. I hope you remember this formula, right? And similarly, I also derived one more formula in this particular chapter, which is RL circuit. In resistance and capacitor circuit, whenever there is a current while charging, IC is given by I naught into 1 minus e raised to t by RC. T by R, sorry, R by L. R by L. So this was the formula which we derived, right? So this is for RC circuit and this is for RL circuit. Okay, so I hope you remember these formulas. Okay, so pay attention. And later on, what the key concept what I'm trying to use is very simple. Okay, I'll put time t is equal to 0 now. Okay, so I'll be doing it for two different situations. One is at time t is equal to 0. At time t is equal to 0, guys, can you tell me by substituting a time t is equal to 0, what will be the value of the current IC? So substitute t is equal to 0 now. Initially, when I'm switching on the circuit, whenever I just switch on the circuit, what will happen to current? So this current becomes I naught into e raised to t is 0. So it becomes the whole thing, t by 0 or 0 by RC into negative 0 is 0. E raised to 0 is how much? E raised to 0 is 1. Therefore, current is equal to I naught. At time t is equal to 0, all the current, the maximum current is passing through it. So capacitor doesn't provide any resistance. The current will directly flow into the circuit. At time t is equal to 0, capacitor behaves as a conductor. It will just pass all the current. Pura current will go into the circuit. Okay, so let us come back and try to solve the same formula for this particular inductor here. So what will happen to the inductor at time t is equal to 0? At time t is equal to 0, the inductor current I naught into 1 minus e raised to 0. Right, the whole numerator will become 0. So what is this? This is I naught into 1 minus e raised to 0 is 1. So 1 minus 1 is 0. 0 into I naught is 0. See, at time t is equal to 0, there is no current passing. No current passing in the inductor. Why it is not passing? Because I already told you, right? The inductor will always try to oppose the motion, so there is no current passing through it. Okay, it behaves like an open circuit. Okay, what happens is there will be resistance, and inductor will become infinite resistor. The resistance बहुत ज़्यादा होगा infinite inductor का, and current will not at all flow in the circuit. I will become 0. I will become 0. Okay, and we'll see after long time. That's very good, guys. Thank you for responding there. Awesome. And let us do it for a time t is equal to infinity. Okay, जब infinity होगा क्या होगा? Then I for capacitor current I naught into minus infinity. Right, infinity divided by RC will be always infinity. Negative sense stays as it is. What is e raised to minus infinity? E raised to minus infinity is 0. Okay, so I naught into 0 becomes 0. See, now it is not allowing current. Now after very long time, the capacitor will behave as an open circuit. After very long, initially it was allowing all the current, but after some time, after very long time, it will not allow any current. It will just block all the current because the capacitor is charged now. जब charge होगा, it will get accumulated positive charge and negative charge. So when the capacitor is completely charged, there is no current flowing from the capacitor. It will completely block the circuit. Okay, and let us see what will happen to the inductor. At time t is equal to infinity, capacitor current will be, sorry, inductor current will be equal to I naught into 1 minus e raised to minus infinity, right? What is e raised to minus infinity? E raised to minus infinity is 0. So what is 1 minus 0 is 1, and I naught into 1 is I naught. See, now all the current is passing, so it behaves as a conductor. It behaves as a conductor, and this is one of the most important concept in solving the problem. And in most all the advanced questions, at least you see one such problem. You're going to see one such problem. Okay, so let me tell you what's going to happen very clearly. Okay, so you take a capacitor and you take a inductor. Okay, so I'm going to make a table, and this table should be there in your mind at all the time, at everywhere. Okay, you should never forget this table. Okay, because this is one of the most basic table in all of current electricity. At time t is equal to 0 and at time t is equal to infinity. Initially, at time t is equal to infinity, capacitor is getting charged. Charging go raha hai, so it will allow all the current. It will allow all the current, and it behaves as a conductor. It behaves as a conductor. So what you can do is you can just remove that capacitor and just write one wire like this. Okay, it behaves as a conductor. At time t is equal to 0, okay, you can just completely remove the capacitor and just write a wire. You can short circuit it. Okay, then you also can solve the problem. Okay, so what happened to capacitor after infinite time? After infinite time, capacitor is completely charged. Okay, charging is completed. Charging is completed. When charging is completed, it will not draw any more current, so it will stop all the current. Current does not flow. Current flow stop hota hai. When current flowing is stopped, you can open the circuit. There is no current passing through it. Okay, you can completely rub that line in which the capacitor was there in that circuit. You can completely rub that line. Okay, so this is what happens after infinite time. And later on, we will come back to inductor. What happened to inductor at time t is equal to 0? At time t is equal to 0, we know that inductor will oppose the current always. So now, since the inductor is opposing the current, it will block all the current. It will block all the current. Okay, so then this becomes open circuit. You can remove that complete line. You can remove that complete line. Okay, what will happen to inductor after very long time? After very long time, when the current becomes stable, when the current is steady, whenever di by dt becomes 0, after when the current is steady, right, then there is no induction, because di by dt is 0 hoga, induced EMF is also equal to 0. Therefore, then it will pass all the current, then it becomes conductor. Okay, becomes conductor. So if you notice, at time t is equal to 0, capacitor was conducting all the current. At infinite time, inductor is conducting all the current. So they behave at different times similarly. And here also, after long time, capacitor was not conducting any electricity, and at initial time, the inductor was not conducting any electricity. Okay, am I clear, guys? So click on yes or no if I'm clear. Yeah. So this is, you can think it as a shortcut trick also, or you can use the formula I is equal to I naught into a raised to minus t by RC, and you can derive the formula also. Come on, respond quickly, guys. If you respond, I'll demonstrate a problem, and we'll wind up the class. Okay, one of the most important concept, right, for advanced students. If you're advanced student, you have to make sure you understand this. YouTube guys, am I clear? Zoom guys, ಗೊತ್ತಾಗಲಿದ್ರೆ ಹೇಳಿ ಆಯ್ತಾ, ಹಚ್ಕೋಬೇಡಿ. Okay, I'll repeat it again if you want me to tell. Okay, so cool then. Cool. Clear. Okay, good. So later on, moving ahead, what's going to happen is, pay very close attention here. I'm solving a similar problem here. Find the equation for current I1 and I2. So they want me to find what is current I1 and current I2, showing its variation with time. So they want me to find what is the current at time t is equal to 0, what is I1, what is I2. Okay, what is I1? I1 is the current passing through the inductor, I2 is the current passing through the capacitor. And similarly, the one more condition is at time t is equal to infinity, what is the current I1 passing through the inductor, and what is the current I2 passing through the capacitor. So they'll ask you such questions. Okay, but I know one thing from the past previous table. I know that at time t is equal to 0, inductor will block all the current. there is no current passing through the inductor, so I can remove the circuit. At time t is equal to 0, there is no current passing through inductor because it is opposing the current. So कुछ भी नहीं pass हो रहा, current flow is completely blocked. There is no current flowing at all, right? Am I clear? See, inductor blocks the change initially, right? Always initially it blocks the current. Here also it is blocking the current. So I'm removing that complete circuit out. So therefore, I1 passing through inductor is equal to 0 because there is no current passing through that. Okay. So let me write the remaining circuit. What is the remaining circuit? There is capacitor, there is a resistor, and there is one EMF. That's all. The middle line is erased because there is no current in that circuit. Okay. What is the EMF here? EMF here is I. What is the resistance? R. Therefore, what is current? Current I is equal to E by R. That's all. Current E2 is equal to E by R. This will be the current for second wire. So therefore, in this particular line, E by R current will be flowing. That's all. Okay. Cool, right? Okay. So similarly, I'll do it for the other case. This is a time t is equal to 0, right? Now I'll do it a very long time after infinite time. What will happen at infinite time? After infinite time, capacitor will block all the current because capacitor is completely charged now. It is blocking all the current. With all the current is blocked, I can remove this completely outside. Therefore, I2 becomes 0 now. The current passing through capacitor is 0. I2 becomes 0, and the remaining current will be how much? So let me write the remaining circuit now. There is inductor, there is resistor, and there is EMF. So the total resistance of the circuit is R. The total EMF of the circuit is E. Therefore, I1 is equal to E by R. Okay, so they're exchanging. Initially, there was current in capacitor. Now the current is in inductor. Initially, there was no current inside the inductor. Finally, there is no current in the capacitor. Cool, right? Am I clear, guys? ಅರ್ಥ ಆಯ್ತಾ? So this, if you know this table now, you can solve it very clearly without any problem. This table you should know. Initially, only remember these two lines. Initially, capacitor will block. No, initially the capacitor will allow the current. Okay, and later on, inductor will allow the current. That's all. Or remember like this: the inductor will block the current at initially because of opposition of Lenz's law. Then later on, capacitor will block the current because of completely charging. That's correct, Jyoti. Yeah, cool. Yeah, that's all. V is equal to IR, V is equal to IR, I is equal to V by R. EMF by resistance is equal to current. Okay, bas. Cool, right? Yeah. Okay. So to take this as homework, try to solve this question. Okay. So here also I'll give you the same idea. So there's a complicated circuit here also. There's a very complicated circuit, but let me tell you, this has a very simple solution. Okay. At time t is equal to 0, what will happen to the circuit? At time t is equal to 0, inductor will block all the current, right? So what I have to do is I have to remove inductor. So you have to remove this wire, have to remove this wire, have to remove this wire. Okay. Now the circuit is incomplete. So let me draw the circuit in a simple way here. So there is 50 ohm resistor. There is one inductor here. There is one inductor here. There is one inductor here. And there is an EMF here. Cool, right? So this is what's happening to the circuit here. At time t is equal to 0, inductor will block the current. No current flowing to the inductor. There is no current flowing to the inductor. There is no current flowing to the inductor. So at time t is equal to 0, the circuit will be open. Right? If the current is not passing through any of this wire, the circuit is not at all closed. So initial current I becomes 0. Very simple. At time t is equal to 0, inductor doesn't follow any current. Therefore, there is no current passing through the complete loop. It becomes 0 current. Okay. After a very long time, this whole circuit becomes conductor, right? This conductor will allow all the current now. जब पूरा current flow हो रहा है, then what will be the current? Then current is equal to potential by resistance. What is the potential? Potential is 20. What is the resistance? Here it is 50 ohm, here it is 25 ohm. They are in series, right? Because see how much current was flowing here, the same amount will flow here also. Because there is no circuit element here. Since there is no circuit element, no drop in potential. So it becomes 50 plus 25. Okay, so do it as a homework. Try to read this very slowly, very clearly, and try to solve this as homework. Okay, guys? Yep. So then this completes the chapter. Okay. So tomorrow there's no class. Okay, since it's the first day of the year, But when we meet, I'll start with electromagnetic waves, and electromagnetic waves will be completed in one day. And if I get one more day time, I'll complete communication system also. Cool, right? So after EM waves, we'll be starting wave optics. When you come back from the exam, we'll start wave optics, and I'll try to complete 3 more chapters before this month end. Cool, right? I hope the speed is fine. Okay. Cool, guys. Cool then. Okay. Take care. See you all. Have a good year. Okay. Have a very good year. Okay. Thank you, Rakesh. Thank you, everyone. Cool, guys. Take care. Okay. Bye bye. If you have any doubts, I have 5 more minutes. I'll be staying here to clear the doubts. If you don't have any doubts, you're free to leave. Okay. Okay. Thank you all. Thank you. Bye bye. But still, I have a doubt. Jyoti, aren't you from 11th? YouTube. Because I saw you in 11th class many times. But why are you attending 12th now? Okay, guys. Cool. Have a good year. See you ahead. I'll be giving two problems as a homework. I'll be putting them, uh, you know, in the notes, in the WhatsApp description, so I can solve them. Okay. Yep. Cool, guys. See you all later. Okay. Bye, guys. Bye, Bhargav. Bye, Madhavi. Bye, everyone from Zoom.